Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Arthur Holly Compton's 1922 publication, A Quantum Theory of the Scattering of X-rays by Light Elements, stands as a monumental contribution to the burgeoning field of quantum mechanics. It provided compelling evidence for the particle nature of electromagnetic radiation, specifically X-rays, and cemented Compton's place in the history of physics. This essay will explore the historical context, the core concepts, the immediate impact, and the lasting legacy of the seminal work. The state of physics prior to Compton's groundbreaking experiment can be characterized by a somewhat uneasy truce between classical wave theory and the increasingly insistent demands of quantum phenomena. Max Planck's explanation of blackbody radiation in 1900, postulating that energy is emitted and absorbed in discrete packets called quanta, had shaken the foundations of classical physics. Albert Einstein, in 1905, extended this concept to light itself, proposing that light also exists as discrete quanta, later termed photons, to explain the photoelectric effect. This notion, while successful in describing certain interactions of light and matter, faced resistance from physicists deeply entrenched in the wave theory of light, which had successfully explained phenomena such as interference and diffraction for decades. The nature of electromagnetic radiation, therefore, remained a subject of vigorous debate. Was it a wave, as Maxwell's equations suggested, or a stream of particles, as Planck and Einstein proposed, or could it perhaps be both? A concept difficult to conceptualize given the deterministic worldview of classical physics. Enter Arthur Compton. Compton, an American physicist, focused his research on the scattering of X-rays, a form of high-energy electromagnetic radiation, discovered by Wilhelm Conrad Röntgen in 1895. X-rays, due to their short wavelengths, proved invaluable tools for probing the structure of matter, particularly through X-ray diffraction. However, the interaction of X-rays with matter presented certain anomalies that defied explanation by classical electromagnetic theory. Classical theory predicted that when an electromagnetic wave interacts with an electron, the electron would oscillate at the frequency of the incident wave and re-radiate electromagnetic waves of the same frequency. This implied that the scattered X-rays would maintain the same wavelength as the incident X-rays, regardless of the scattering angle. Compton's experiments, conducted at Washington University in St. Louis, meticulously examined the scattering of X-rays by light elements such as graphite. What he observed was startling. He found that the scattered X-rays exhibited a wavelength shift dependent on the scattering angle. This meant that the wavelength of the scattered X-rays was longer than the wavelength of the incident X-rays, and the magnitude of this shift increased with an increase in the scattering angle. This phenomenon, dubbed the Compton effect, was completely inexplicable by classical wave theory. To explain this peculiar phenomenon, Compton turned to quantum theory. He treated the X-ray as a stream of photons, each carrying energy E and momentum p, related by the equations E equals h nu, where h represents Planck's constant and nu represents the frequency, and p equals h nu over c, where c represents the speed of light. He then modelled the scattering process as a collision between a single photon and a single, initially stationary, electron, governed by the laws of conservation of energy and momentum, the same laws that govern collisions between billiard balls. By applying these conservation laws and using relativistic mechanics, Compton derived a formula for the change in wavelength, delta lambda, of the scattered photon. The resulting equation, delta lambda equals h over m sub ec times 1 minus cosine of theta, where m sub e represents the rest mass of the electron and theta represents the scattering angle, perfectly matched his experimental observations. This equation, now known as the Compton scattering formula, is a cornerstone of quantum mechanics. In essence, the Compton effect demonstrated that when an X-ray photon collides with an electron, the photon transfers some of its energy and momentum to the electron, causing the photon to lose energy and, consequently, increase in wavelength. The amount of energy and momentum transferred depends on the scattering angle, hence the angular dependence of the wavelength shift. This was a definitive confirmation that X-rays, and by extension, electromagnetic radiation in general, exhibit particle-like behavior. The immediate impact of Compton's discovery resonated deeply within the scientific community. It provided compelling, arguably irrefutable, evidence for the quantum theory of light, solidifying the concept of the photon. Prior to Compton's experiment, the photon hypothesis, while useful, was still viewed with skepticism by many physicists. Compton's work removed much of this doubt and spurred further investigations into the quantum nature of light and matter. It strengthened the budding field of quantum mechanics, which was still struggling to gain acceptance. The Compton effect also had practical implications. It became an important consideration in the design of X-ray equipment, particularly in medical imaging and radiation therapy. Understanding how X-rays scatter in matter is crucial for developing effective shielding techniques and minimizing radiation exposure to patients and medical personnel. Furthermore, the Compton effect found applications in various fields, including materials science, where it is used to study the electronic structure of materials, and astrophysics, where it plays a role in the interaction of high-energy photons with matter in space. The Compton effect has served as a foundation for numerous subsequent discoveries and technological advancements. One notable example is the development of detectors that utilize Compton scattering for gamma-ray imaging in medical diagnostics, such as positron emission tomography, or PET scans. These detectors exploit the fact that gamma rays, similar to X-rays, undergo Compton scattering when interacting with matter. By carefully analyzing the scattered photons, it is possible to reconstruct an image of the distribution of radioactive traces within the body, providing valuable information for the diagnosis of various diseases. Furthermore, Compton scattering plays a crucial role in understanding the interaction of high-energy photons with matter in astrophysical environments, such as in active galactic nuclei and supernova remnants. In these environments, photons can undergo repeated Compton scattering, leading to significant changes in their energy and direction. This process, known as Comptonization, is important for understanding the observed spectra of these objects and for probing the physical conditions in these extreme environments. The reception of Compton's work among physicists was mixed, as is often the case with revolutionary scientific discoveries. While some embraced the Compton effect as strong evidence for the photon theory, others remained skeptical, clinging to the classical wave theory. Some questioned the accuracy of Compton's experimental measurements, while others challenged his theoretical interpretation. For instance, some physicists proposed alternative explanations for the observed wavelength shift based on modifications of classical electrodynamics. However, the weight of experimental evidence gradually shifted the consensus in favor of Compton's interpretation. Further experiments, conducted by Compton himself and by other researchers, confirmed the validity of his results and the accuracy of his scattering formula. Moreover, the Compton effect found support from other areas of physics, such as quantum electrodynamics, which provided a more complete and rigorous theoretical framework for understanding the interaction of light and matter. In 1927, Arthur Compton was awarded the Nobel Prize in Physics for his discovery of the effect named after him. The Nobel Prize served as a definitive validation of his work and solidified its importance in the history of physics. In his Nobel lecture, Compton eloquently summarized the significance of his discovery, stating that it provided direct experimental proof of the quantization of electromagnetic radiation and opened new avenues for exploring the quantum nature of the universe. Compton's work did not occur in a vacuum. He was influenced by the work of Max Planck and Albert Einstein, who had laid the foundations for quantum theory. He built upon their ideas and provided crucial experimental evidence that supported their theoretical predictions. Similarly, Compton's work influenced many subsequent researchers, including Paul Dirac, who further developed the theory of quantum electrodynamics, and numerous experimental physicists who continued to explore the interaction of light and matter at the quantum level. The influence continues to this day. Researchers continue to investigate Compton scattering and its applications in diverse fields. Advanced mathematical techniques now allow physicists to model complex scattering scenarios, including those involving relativistic electrons and intense laser beams. The study of inverse Compton scattering, where a low-energy photon gains energy by scattering off a relativistic electron, has become an essential tool in astrophysics for understanding high-energy phenomena. A quantum theory of the scattering of X-rays by light elements stands as a testament to the power of scientific inquiry and the importance of challenging established paradigms. It represents a pivotal moment in the development of quantum mechanics, bridging the gap between classical and modern physics. Compton's meticulous experiments, insightful theoretical interpretation, and unwavering commitment to scientific rigor paved the way for a deeper understanding of the fundamental nature of light and matter, transforming our view of the universe at its most elemental level. It is a truly remarkable contribution, one that has earned its place among the pantheon of scientific achievements. The wave-particle duality, a concept so counter-intuitive it likely sent shivers down the spines of even the most seasoned physicists, found its strongest support in this work. Moreover, Compton's work serves as a reminder of the interconnectedness of scientific disciplines. His research on X-rays, originally motivated by questions about the structure of matter, led to profound insights into the nature of light and the fundamental laws of physics. This underscores the importance of interdisciplinary research and the potential for unexpected discoveries when scientists from different fields collaborate and share their expertise. Arthur Compton made a contribution that continues to resonate through modern physics. In conclusion, Compton's 1922 paper represents far more than a mere experimental result. It represents a paradigm shift in scientific thinking. It provided unambiguous evidence for the particle nature of electromagnetic radiation. It advanced the quantum theory. It continues to affect modern technology. Its significance reverberates throughout scientific literature. The enduring impact of this contribution warrants continued examination and appreciation for its role in transforming modern physics.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.